Hello, y'all. Barry Berry Jr. here. I'm back for some more impromptu physics. So I'll actually study my graduate school mechanics textbook. I've been focusing on my redoing my exam for my foundations class recently. So I was reading some undergraduate, but I want to make sure I keep up with the new stuff that we started recently, which is something I actually am familiar with from quantum mechanics, and not quantum mechanics, uh, uh, astrophysics. So astrophysics, we actually um, did, I don't remember the exact name of the process, but basically working out metrics is the word, different metrics for different types of space. So during that process, I took the effort to derive the Lagrangian through variational principle. Even though I don't remember all the details, I couldn't do it by heart right now or something, but um, it was So it was fun to do. And I was able to get a background information on the variational principle and how Lagrange relates to that. So that's something that will be covered on Friday in class. So that's what I'll do is go through the book sections in question and perhaps go through the notes that we had in class, but that'll be another video. And I still want to do some more of the examples of Lagrange from the first chapter. So that'll be another video as well. So for right now, this is the book and chapter, Variational Principle, Chapter 2, Goldman's book. And that looks good. So we have 2.1. The derivation of Lagrange's equations presented in chapter 1. I actually did part of that yesterday, if I recall, up until the part right before we subtract a v. So if you look at yesterday's video, you should be able to see the first like 4/5 of the derivation from chapter 1, starting from a consideration of the instantaneous state of the system and small virtual displacements about the instantaneous state, i.e., from a differential principle such as the Lambert's principle. So the way my professor described it in class is like if you have a curved path and we have a um, critical point where this is f of x df dx, where that equals 0, the slope is 0. And if you have a stable critical point and you move just a little bit to each side, it's basically, it doesn't really change the physics so much, you know. And it also reminds me of how around a stable point you get simple harmonic motion, back and forth. So, but basically we have a point, and around that point we have stability. What this is going to do is we're going to have a path, and we're going to have another path that changes ever so slightly from that path, but not so much where it makes a big difference. And that's how we're going to derive more principles from that. It is also possible to obtain Lagrange's equations from a principle that considers the entire motion of a system between times t1 and t2, and small virtual variations of this motion from the actual motion. A principle of this nature is known as an integral principle. Before presenting the integral principle, the meaning attached to the phrase motion of the system between times t1 and t2 must first be stated in more precise language. The instantaneous configuration of a system is described by the values of the n generalized coordinates and correspond to a particular point in a Cartesian hyperspace where the q's form the n coordinate axis. It's interesting. So we have, recalling from before, seems like they're saying we have R and we have Q1, Q2, and on to Qn, and perhaps T. And the hyperspace would be, so in our three-dimensional system, we have three axes that are all at right angles to each other. It seems like they're saying, imagine if we have multiple axes that are still all right angles to each other. And now we have Q1, Q2, Qn, and T. That's what it seems like they're saying. This n-dimensional space is therefore known as configuration space. As time goes on, the state of the system changes and the system point moves in configuration space, tracing out a curve described as the path of motion of the system. The motion of the system, as used above, then refers to the motion of the system point along this path in configuration space. So the point at time t, as that point moves through the system currently. Time can be considered formally as a parameter of the curve. To each point on the path, there is associated one or more values of time. Note that configuration space has no necessary connection with the physical three-dimensional space, just as the generalized coordinates are not necessarily position coordinates. This is configuration space. The path of motion in configuration space has no resemblance to a path in space of any actual particle. Each point on the path represents the entire system's configuration at some given instant of time. All right. That seems very conceptually abstract, but it is not necessarily a space, but each point represents the configuration of the system at some point in time. The integral Hamilton's principle describes the motion of those mechanical systems for which all forces except the forces of constraint are derivable from a generalized scalar potential that may be a function of the coordinates, velocities, and time. Such systems will be denoted as monogenic, but the potential is an explicit function of position coordinates only. Then a monogenic system is also conservative. For monogenic systems, Hamilton's principle can be stated as, so I remember her mentioning monogenic. She explained it a lot better. Monogenic, the motion of the system from time 1 to time 2 is such that the line integral remember this term action integral. I always write the Lagrangian L like the cursive L. As a stationary value for the actual path, the monogenic motion of system from time 1 to time 2 is such that the line integral or the action integral, which is the integral of the Lagrangian from T1 to T2, has a stationary value for the actual path of the motion. That is, out of all possible paths by which the system point could travel from its position at time T1 to its position at time T2, it would actually travel along that path for which the value of the integral to 1 is stationary. Monogenic stationary value. By the term stationary value for a line integral, we mean that the integral along the given path has the same value to within first order infinitesimals as that along all neighboring paths, those that differ from it by infinitesimal displacement. So this goes back to the idea of a small change from that stable equilibrium point doesn't really change much. The notion of a stationary value for a line integral thus corresponds in ordinary function theory to the vanishing of the first derivative. Okay. We can summarize Hamiltonian's principles by saying that the motion is such that the variation of the line integral I for fixed T1 and T2 is 0. So variation of the action integral equals variation of T1, T2, and we have L, Q1. Okay. I'll just say QI, Q dot T dt equals 0. And that's what I was thinking they meant when they said the vanishing of the first derivative, but I would have wrote it as d of dt, but then I was looking at the dt for the integration. You notice that the q's, there's a whole string of q's. The q dots, there's a whole string of q dots, but there's just one t. Where the system constraints are holonomic, I don't remember what holonomic means. Oh yeah, equals 0. It can be written in the form where the function of it equals 0. Hamilton's principle. So this is Hamilton's principle. Is both a necessary and sufficient condition for Lagrange's equation 1.57. And Lagrange's equation is d dt partial swigly L over partial q dot I minus partial swigly over partial qi equals 0. 7. Thus, it can be shown that Hamilton's principles follow directly from Lagrange's equations. Instead, however, we shall prove the converse, namely that Lagrange's equations follow from Hamilton's principle as being the more important theorem. So I'm not clear which one they're saying is the most important principle, Lagrange or Hamilton. It's just saying Hamilton is the most important. The Hamilton's principle is a sufficient condition for deriving the equations of motion. That Hamilton's principle is a sufficient condition for deriving the equations of motion enables us to construct the mechanics of monogenic systems from Hamilton's principle as the basic postulate rather than Newton's law of motion. Such a formulation has advantages For example, since the integral I, the action integral, is obviously invariant to the system of generalized coordinates used to express L, the equations of motion must always have the Lagrangian form no matter how the generalized coordinates are transformed. More importantly, the formulation in terms of a variational principle is the route that is generally followed when we try to describe apparently non-mechanical systems in the mathematical close of classical mechanics. Apparently, variational principle works with fields. I remember a professor saying how Lagrangian, and textbooks said it as well, how the Lagrangian can help with EM as well with fields. Right? We got through the first section. Next time I do this part, I'll probably do some of these techniques. I noticed that they drew the graph I was thinking about here. I can actually just add this here. So if I have a path going through this space, T1, T2, and the variational will be these paths that end at the same place. So it's important that the start and end of the varied paths is the same as the original path. But the idea is that long as the variational path is not that different, we can derive some things. So next time I pick up from here, I'll start with some techniques of calculus of variations, which is actually what we did in class. And I'll see if I can come to the same conclusion. Usually the book is not as clear as the professor. Of course, it does help, but also a different perspective. But I'll have my notes from class up as well, and I'll see if I can put them both together and derive this for you all. So it'll probably be after my the problems I'm going to do, or at least the problems I'll do in mechanics for, what was it? Centrifugal force, I believe I'll do. So you can see it's scheduled. So I'll probably do some centrifugal force problems, and later tonight do some variational calculus of variations, and we'll keep it rocking. So I'll try to keep the weekends busy. I'm usually very busy during the week in classes, being a teacher's assistant, and meetings and stuff that goes on with research, all fun stuff. So it's good to be happily busy doing things I enjoy, but just can't make videos as often as I might otherwise. Plus, I don't want to bother people. There's other grad students here and stuff. But usually on the weekends, everybody else is like doing other things. So thanks everybody who watches. Make sure you like and subscribe if you haven't. Help me get to 1,000 subscribers. Share. Be sure to put a comment on the video or on the poll in the post section to let me know what things you'd like me to cover. And I'll see y'all next time.